Welcome to the third lesson here of Unit 2. Our essential question for the unit is how do the properties of subatomic particles determine the different chemical properties displayed by atoms of each element? And a daily question is how does the nucleus remain together despite containing protons which should repel each other? And if you remember back to our lesson 2 days ago, James Chadwick, amongst other scientists, really wondered this. Protons are positively charged, they shouldn't all just be together in the nucleus. And if they are, there must be some force that holds them together. Well, there is, and it's related to the concept of mass effect. So that's where we'll start today. When an atom is formed, a small amount of matter is converted into energy. We should also remember from the law of conservation of mass, we just got done saying that can never happen, that mass is always conserved. And it is almost all of the time, except in reactions that we tend to call nuclear reactions. So Albert Einstein had a hand in this. He developed a relationship between energy and mass in 1905, the E equals mc squared. That's energy equals mass times the speed of light squared. And it can be used to calculate the binding energy for a nucleus. What is this energy, this nuclear energy, holding the atom together? So it explains why an atom's actual mass is going to be slightly less than the mass number. This is an observation that scientists have found. And so as a nucleus forms, mass is converted to energy. The lowered energy of the nucleus makes it more stable. And in order to disrupt the system, you would have to add back the original energy lost. A couple other definitions here. The nuclear binding energy is the energy released when the nucleus forms, or the force that holds the nucleus together. And the binding energy per nucleon, the binding energy divided by the number of nucleons. So we can see from these definitions, and if we extrapolate a little bit, some atoms are more stable than other atoms are. And so typically nuclear reactions kind of follow this stability pattern where unstable nuclei can be broken apart, but then they'll reform a more stable nucleus and it ends up releasing energy. This is how the nuclear bombs and nuclear power plants work according to E equals mc squared. It's also how our sun works, by taking hydrogen atoms and forming them into more stable helium atoms. And eventually at the end of a star's life, it takes helium and burns that and converts it into larger and larger elements until iron is produced, which I believe is the most stable element in terms of nuclear chemistry. So the best way to learn about these types of problems is really just to do them. So we've got a question. Determine the mass defect, the binding energy, and binding energy per nucleon for chlorine 35. Which has an atomic mass of 34.99 AMU. So the first step here is just determining the subatomic particles. Chlorine has 17 protons. How did I know that? From the periodic table. We're going to look at the isotope chlorine 35 here. So 35 minus 17 gives me 18 neutrons. And we'll assume that all of these are neutrally charged. So the electrons should always be the same as protons in these problems. Now, the next step here is to calculate what the mass should be for this chlorine 35 atom. It should be 17 protons times the mass of the proton, 1.007276 AMU. This mass of the proton, it will be given to you anytime you have to do a problem like this, so you don't have to memorize it. We're going to add to that the 18 neutrons times the mass of the neutron, the 1.008665 AMU. And then we'll add the mass of the electrons times the number of electrons there. So you can see the three terms here. I added those all up, and we got 35 0.2889882. I always think it's a good idea to leave all your decimals in place until this point. Now later in the year we'll learn about significant figures, but for the purpose of this problem, if the mass that I'm given in the problem was 34.99, I want to at least keep this at 35.28, which would then become 35.29 because of the 8 following it there. So I want to at least have the same number of digits in this step as I do in the mass that I'm given. So if I had a longer number, then I'd want to keep more digits in. Because my next step is to take that 35.29 AMU minus 34.99 AMU. That gives me a mass defect of 0.30 AMU. So we've got the first answer there. We got the mass defect. Now, we want to start thinking about binding energy, but in order to do that, we have to convert from AMU here to kilograms. Now, the conversion for kilograms to AMU is that 1 atomic mass unit equals 1.66054 times 10 to the negative 27th kilograms. So if I take a number like 0.30 AMU, I'm going to multiply by 1.66054 times 10 to the negative 27th kilograms over 1 AMU, and the AMUs would actually cancel out there, and I'm going to be left, if I do that math, with a number in kilograms. Please make sure you're doing this on your calculator. Please punch this in on your own and be checking to make sure you get a similar answer to what I have. If you're not getting a similar answer, certainly ask about that in class as we're working on the problems tomorrow. So we should have 4.96 times 10 to the negative 28 kilograms. You might be slightly off of that because of some rounding or something, but just make sure that you're somewhere close to that. Certainly on the order of 10 to the negative 28th. Now, we're going to plug this in to Einstein's equation E equals mc squared. The m is now 4.96 times 10 to the negative 28th kilograms times c, which is 3.00 times 10 to the 8th, but that is squared. So this calculation is a little tricky. If I was typing this into my calculator, I might take 3.00 times 10 to the 8th, square it, then multiply by the 4.96 times 10 to the negative 28th. That's the only, you want to make sure at the end you get the 4.47 times 10 to the negative 11th, and I think that's the best way to do it. As far as units go, units are really important in science, so we want to think about that. I'm taking a unit of kilograms and I'm multiplying it by a meter per second squared. So the unit for this would actually be kilograms times meters squared divided by seconds squared. We've just called that a joule. So a joule is the same thing as a kilogram meter squared per second squared. The math that you apply to the numbers, you do the same thing to the units. So that's what you'd have there. 1 joule equals 1 kilogram meter squared per second squared. That is the binding energy now. So we have the binding energy, but this question asks us for the binding energy per nucleon. So it's going to be 4.47 times 10 to the negative 11th joules divided by 35 nucleons for 1.28 times 10 to the negative 12th joules.